We first give an overview of features that we compute within a single frame. Where noted, we make use of several feature computations provided by the public implementation of Sapp, Toshev, and Taskar from 2010. The first feature we use is histogram of gradient-based limb detectors for the upper and lower arms. These provide scores for 24 different angles at each location in the image. For any pairwise shoulder-elbow or elbow-wrist pair, we compute the score of the closest of the 24 discretized angles. We also use these as unary features by taking the maximum score over all angles at each position. Here, we see the relative weakness of the lower arm detector relative to the upper arm detector when we maximize over angles. We next incorporate a measure of contour support to detect limbs. We extract contours from an oversegmentation of the image. As seen here, the contours are very sparse. For each possible limb location, we compute the number of close contour points that are roughly parallel to the joint pair line segment. Even though the number of possible joint locations is large, the number of joint pairs with contour support is small, and therefore we can compute this feature efficiently. Here we see supported line segments for the lower arm in a sample of the test set. Because the torso and head are already roughly localized, we can reliably get an estimate of skin color from the face and clothing or body color from the chest. Torso color is a strong localization signal for the shoulders and elbows. Skin color is also a strong signal for wrists and elbows. Because detecting the hand location is an extremely useful cue in anchoring all joint locations, we improve the basic skin response map by learning a linear filter color-based hand detector. After convolving the skin response with our hand filter, we obtain an image that is significantly more informative than the original map. Finally, the last color-based feature is a color correspondence measure between areas around the left and right joints of a person. For each joint, we extract a small patch, and we compute chi-squared distances between the color histograms of each patch. Here we see the correspondence scores between the left hand and all possible right hand locations. Color correspondence is a powerful new feature that has not previously been explored. In addition to these color-based features, we also incorporate a few simple geometric features. A feature for the coarse 2D location of each joint, a feature for the shoulder angle, and a feature for the X distance separating the elbows and hands. We now turn to features that we compute between consecutive frames. As shown here, we compute the magnitude of the optical flow throughout the entire dataset. We then extract motion discontinuities by computing the gradient magnitude of the flow field. We use these motion edge maps in two ways. First, we augment our contour features by additionally computing only contours that are supported by flow edges. Next, because hands are often moving, we learn a novel flow-based hand detector that detects hand-shaped motion discontinuity. We learn a linear filter similar to the color-based hand detector that gives additional cues for hand location. Note that the signal from the hand detector is occasionally very strong, but it is also very unreliable from frame to frame. This is one reason why tracking is so important. For tracking, we capture the persistence of appearance over time with a simple yet very effective patch-based color tracker for each joint. For each joint, we compare patches extracted around the joint in each frame to patches extracted around possible locations for the joint in the next frame, using a robust, quantized L0 distance function. The L0 distance is both resilient to changes in lighting and pixel fluctuation and much more discriminative than color histograms because it takes into account pixel structure. Here we see the L0 distance from the left-hand ground truth location to all possible locations in the next frame. We combine these tracker features with a simple Euclidean distance between two consecutive points to emphasize smooth trajectories. If a point can be properly localized in at least a few frames, these tracking features provide a powerful and accurate signal for the intervening frames.